So to get a well-defined theory, so what does this mean? It means that instead of imposing commutation relations on the fields, we impose anti-commutation relations. People come across these squiggly brackets before in the context of quantum mechanics? Oh, good. Okay. So let me just write the definition. So the anti-commutator means there's a plus there instead of a minus. Okay. If we do that, and then we plug these guys in, you could show that all the B's anti-commute with each other. Well, actually, let me write everything down. Okay, actually there's many more, I guess. All the B's and C's also. Everything other than these is vanishing. Yeah, Ross. Did I make a mistake? CQ.
So they don't really anti-commute even if this is different on them? There's no...
There's a delta RS, yeah, thanks. Yeah.
Is that a question?
Oh, okay, yeah.
Sorry, yes. Okay, notice that there's no minus sign here. The B's and the C's are on the same footing. Again, it's a tedious calculation. Just sit down. We can now go through and compute the Hamiltonian. And after normal ordering, this annoying minus sign goes away. I should say that we're also spinning over spins here, summing over spins here. Actually, it's worth me stressing something here. Before I normal order, I get the usual infinity. But it is worth stressing that this infinity comes with a minus sign, whereas the infinity that we got from bosons came with a plus sign. Okay? So and for free theories, we can always normal order, and this is not really relevant. But when you come to think about, well, I mentioned this in the bosonic case, coupling to gravity, these terms should be contributing to the cosmological constant, and actually giving a contribution to the cosmological constant much greater than what we see. Somehow that's got to be cancelled by something else. Well, here there's a nice observation. It's that the contributions to bosons cancel the contributions to fermions. So if you can somehow arrange to have equal numbers of bosons and fermions in your world, then things will cancel. Okay? And actually, that's what supersymmetry does for you. So if you have a supersymmetric theory, you get exact contributions, exact cancellations between bosons and fermions. A supersymmetric theory is a theory that has, if you like, equal numbers of bosons and fermions, but also having related interactions to each other. Okay? So there's that minus sign that does that for you. Okay, so what we're seeing here is sort of the moral of the spin statistics theorem. It's that in quantum field theory, you don't really get a choice about which statistics you put on fields of a given spin. If you try to quantize spinors as bosons, you won't get a consistent theory. You'll only get a consistent theory if you quantize them as fermions. Similarly, if you try to quantize, say, a spin zero particle in this way, you again won't get a consistent theory. Things go wrong. So you're sort of forced into picking the statistics given the spin of the particle. Questions about this? No? Let me just sort of illustrate more explicitly why this means that we're quantizing in astronomy. It's fairly straightforward, but it's important to do it. So we can introduce the usual kind of Fock space. So the vacuum is defined as the state which is killed by all the annihilation operators. So there's an infinite number of annihilation operators now, because they're labeled by 3 making P, but there's 2 of the particles, which you could think of as spin-ups, and there are 2 fermions. Questions?
So what are those annihilation operators do?
Yeah, okay, so let me say,
that equation looks really close. Maybe we should take an order down. Okay, thank you.
I have a real problem with adding equal 0 at the end of most equations. So if there's never it's always an equal 0. There should be some notation to that. This equation, you don't have to write an equal sign. You just write down something. It's assumed it's equal 0.
But you had an equal sign. But you had an equal sign.
Yeah, but I think just remove that. They both equal 0. I think it's a breakthrough.
Maybe put an equal sign with no 0, but that should be like notation for.
Yeah, but later, why have the equal sign at all? Everything's equal to 0 in math anyway. Okay, so yeah, let me just mention that you can check. Every time I say you can check, this should be interpreted. You should check. These really are creation and annihilation operators in the way that we used to, even though they made these anti-commutation relations rather than commutation relations.
So those are supposed to be commutators?
Yeah, so what do they do with H? You've got an anti-commute. Okay? Because of the same reason you're supposed to anti-commute. So this has the interpretation that acting with this raises the energy of a state by
Right.
and this lowers it. But that interpretation requires anti-commutators. Sorry, requires commutators. That part. There's a way to think about what sort of commutators you should put on things. You can really, all operators you could either think of as being even or odd, where even are the kind of operators you're used to, they commute, or they have certain commutation relations. And then odd, they're these new ones, they're the ones that have anti-commutation relations. And then the question is, what do you do if you have an odd with an even? This is what we've got here, an H, which is very normal, and B. So this is even and this is odd. And then you do commutation relations. Okay, so then this will come up again and again.
We may have to talk about this later, but there seems to be that because the anti-commutation relationships are symmetric between B and B dagger, there seems to be an arbitrariness in defining the vacuum. Can we?
I don't think that's true because it's not symmetric here. So it's a question of not what B and B dagger do themselves, but what they do with H. And there's a minus.
How does that come about if what we imposed is symmetric?
What we imposed was symmetric, but what was the right way
Oh, with the Lagrange.
H knows, right? There's an ordering in H as to whether you assign dagger or electron. And if you change that ordering, you pick up a minus sign because they have to use it, so it goes minus H. And that's the same minus sign we see. Okay, so it's really with the definition of H.
Yeah, that's right, because we normal order things with a H.
Yeah. Okay. Good. So these create states that have this energy. It's the same argument we saw for the bosonic case. So we have first example, one particle states. Of the form BPS dagger acting on a vacuum and CPS dagger acting on a vacuum. Okay. These are going to be interpreted as antiparticles. These are going to be interpreted as, sorry, I said that the wrong way around, particles and antiparticles. That's exactly the same as we saw for a complex field. What's new is this S index here. And this is going to determine the spin of the particle. Okay? So let's look at where it came from. The S index for the creation and annihilation operator is kind of linked to which particular spinner we're thinking about. And that's a little bit arbitrary. Okay? So the S equals 1, 2 index tells us the spin. So you could ask, spin in which direction? Okay, spin up, but if it's spin up, I really mean spin up in the z direction or in the x direction. It's usual quantum mechanics. So that information is sitting in these spinners here. Okay, so let me give an example, and then hopefully it should become clear. So this guy here is a 4-component spinner. That's a fixed, for a given momenta, it's a fixed 4-component spin. Okay, this is what we saw in the last lecture. Did you guys manage to show that this solves the Dirac equation in the last lecture? Some of you and some not. Okay. And we introduce a basis here. So this is now some two-component object. And now we do the usual game of quantum mechanics. So if we pick zeta 1 equals 1, 0 as a basis, and zeta 2 equals 0, 1, the s equals 1 and the s equals 2 particles have spin up or spin down, respectively, in the z direction. Okay? So you pick a basis for the size, the little two-component spinners, that's your definition of U. If we've picked this basis, then these are eigenstates of the third Pauli matrix, which is why this is spin up and this is spin down in the z direction and not the x or y direction. And then because this S index here gets correlated with these creation operators, B1 dagger creates this guy, and B2 dagger creates this guy. Okay, so you can spin up, spin down accordingly. Is that clear? Yeah. Okay, so once we've got sort of this stage, we're basically at the usual quantum mechanics discussions. Okay, but now notice that if we create two particles, with two different spins and momenta P1 and P2. Okay, so we have to label the states. Yeah, we have to label the states now by both the momenta and the spin. But this is equal to minus the state if we do them the other way around, and the reason is that these two anti-communicate each other. So this is exactly what we mean by Fermi-Dirac statistics. Okay. Are there any questions about this?
Is there a physical reason why in the Hamiltonian we got the minus sign? Like,
When we try to do them as bosons?
right.
Yeah, the physical reason is that you missed something really crucial.
Well, no, even before, even without doing it as bosons, because before you normal order, you still have a minus sign, right?
Minus sign in the sort of that minus or constant piece.
We have minus CC dagger
Minus
in the Hamiltonian.
C dagger. Yeah, but if you write the Hamiltonian as C dagger C.
Right. Then,
Right,
but
C dagger C is the thing that counts the number of particles. So that's the thing that should come in the plus sign. So a sensible Hamiltonian has plus C dagger C, but then if they're fermions, that means it has minus CC dagger. So in some sense, that minus sign is there because the theory didn't make sense for fermions. Other questions? No? Okay, what I want to do briefly now is tell you how this contrasts with Dirac's original picture of antiparticles and such like. Partly because some of you may have seen this story before. It's sometimes taught in undergraduate. Who saw the Dirac equation before they came here, interpreted as a wave function Yeah, okay, good. So it's worth sort of going through that because that's completely wrong, okay? You know, it's like when we teach physics, we always lie to students, you know, all the time, and then you get caveat after caveat after caveat. So this is a really key example where you've been lied to, and it's worth now unremembering what you learned before. So Dirac's Hall interpretation. Okay, so when Dirac originally came up with his equation, he wrote it in the following form. Okay, so this is the way we've been writing it. Dirac wanted it to look like a Schrodinger equation. Okay, so there is a deep psi by dt coming in here, but it's got a gamma 0 multiplying it. So we're going to take this equation, and we're going to multiply it on the left by gamma 0. Gamma 0 squared is 1, so that leaves us with this, but all the other terms come with a gamma 0. Okay, so often in textbooks, it's written in the following way. These alpha matrices is just gamma 0 times our gamma matrices, and this beta matrix is just gamma 0. Okay, so it's clear that we get this from that. Now, written in this way, Dirac wanted to do something which with hindsight is not correct, but it's still what's often taught as at the undergraduate level, which was to interpret this field here as the wave function for a single particle moving in space. Okay? So it's not something which anti-commutes or anything like that. It's not an operator in Dirac's language. It's just the kind of wave function that you learn when you first learn quantum mechanics. This is then identified as the Schrodinger picture. Sorry, as the Schrodinger equation, where this is thought of to be the Hamiltonian, which I'm going to call H hat, acting on this wave function. Okay, so old school quantum mechanics. Yeah? This Hamiltonian H hat is not the Hamiltonian we've been considering. Okay, it's a Hamiltonian. It's given by this. It's not the Hamiltonian that we've got, which is sort of the Hamiltonian for the field. Okay, it's the Hamiltonian for this. When you have this interpretation, so with the interpretation of psi as a wave function, and in particular as a one-particle wave function, then we can look at the solutions which we found in the last lecture. So we had two solutions. One I called positive frequency and one I called negative frequency. They were given by this. These u's and these v's are these fixed vectors. And the Schrodinger equation tells you the following. It tells you that these guys here should be interpreted as having positive energy, and these guys here should be interpreted as having negative energy. Okay? Again, this is not the right interpretation, and it's not what we've seen when we think of this as a field. When we think of this as a field, we made sure the Hamiltonian was positive definite, okay, as long as these things were treated as fermions. So this is if you interpret psi as a wave function, you find positive and negative energy states. Okay, so the spectrum looks like the following. Here's the energy, and this is 0. So there's a gap. The first state appears at plus m, and then there's sort of a continuum of states because the momentum is continuous. Okay, if I put the particle in a box, it would be discrete, but it's a continuum if I'm in flat space. And then there's another set of states here whose energy starts at minus m and goes down to infinity. Okay, so this looks bad again. It's the same kind of problem we thought we had when we quantized the particle as a boson. Okay. But Dirac wasn't daunted. Dirac came up with the following ingenious argument. He said, our particles are going to be fermions, because they're spin half, and that for fermions, the Pauli exclusion principle holds, and I can't put a fermion twice in the same state. So he said, suppose that all these states here, all infinite number of them, already have fermions in, going all the way down to infinity. Then there's no way we can put another fermion in there, and all excitations of fermions have to live up here. So Dirac's argument was that all of these states were filled, and somehow, you might think, but that's an infinite amount of energy. Dirac said, well, we only really care about energy differences, so what we call 0 is basically this infinity. And it sort of smells at a lot of the things that come up in quantum field theory, right? Normal ordering, renormalization. So he said, well, we should only have access to these states. But then he noticed something quite brilliant. He said, suppose that one of the particles that was filling this state actually gets excited and comes up here, so that there's a particle missing down here. In a condensed matter context, we'd call this a hole instead of an electron. He noticed that the properties of this hole that's missing from this Dirac sea would be those of a particle that had the opposite charge to the actual electron, and what's more, could annihilate with the actual electron, because this is an electron and this is a hole, and this guy can jump back down there and annihilate. So this was how Dirac came upon this idea of antiparticles, was through this interpretation of these negative energy states as being filled because they were fermions, and this idea of the Dirac sea. I don't want to write all that on the board. Is that OK if I just don't write that on the board? It's all in the notes. Yeah. I'm not good with essays. It's a beautifully ingenious idea, right? But it's not the right interpretation of this equation. For example,
like when you compare to see some of the negative energy particles around, what would they look like?
They look like positons. You don't see them if they're all full. Because you argue that we just get used to them. Maybe you want to say, and the only thing we notice in the physical world is so it looks like there's an infinite negative charge here. Dirac said that's okay. All we notice is differences from that infinite negative charge. It's not dissimilar from ideas of renormalization. Infinite negative energy. They can't move anywhere, so we wouldn't see them. They can't move because to move means changing their momentum, but all the other momentum states are already filled and they're fermions. So we only see them if they move up to here, and then they're interpreted as antiparticles. Is that answer your question?
I find that very satisfying. So why is it the wrong interpretation?
Good. Why is it wrong? This is an argument for antiparticles that only works for fermions. Antiparticles are there for bosons and so that's one killer argument. Antiparticles are also there in quantum field theory. But then there's no issues of filling an infinite sea of states. What this is really telling us, it's something I was stressing at the beginning, that if you combine special relativity and quantum mechanics you can't have single particle states. At least you can't restrict yourselves just to look at single particles. And that's what we're seeing here. We thought we were writing down a wave function that described just one particle movement. But we've learned already that, well, there's at least an infinite number of particles here, and that this quantum mechanical system should be able to excite any number of these up here. What this is telling us is that once you get a combination of special relativity and quantum mechanics, you're obliged to consider states that have arbitrary numbers of particles. And the right framework to do that is quantum. As you say, Dirac didn't give up on this idea as he was dying dead. I mean, in the 1970s, he was unwilling to believe in quantum field theory. We had QCD, we understood mesons, we understood baryons. He didn't believe it precisely because this argument didn't work for mesons, which also had antiparticles. He wanted to rectify this. I should also say that in the context of condensed matter, this is exactly what happens. And there it's called the Fermi C instead of the Dirac C. But there it's really the right interpretation.
Were their own antiparticles, and therefore,
I suspect not, actually. I suspect it's still...
I mean, what I'm saying is that the argument against this picture is that you cannot have a single particle interpretation of the Dirac equation. Does that statement break down for Majorana particles? Have you thought about that?
No, that's certainly still there for Majorana particles. You can start creating arbitrary numbers of them, because there's no conservation law at all against the creators. Okay. What to say? The way that quantum field theory was discovered was sort of through these kind of ideas, noticing that the Dirac equation that we thought was a wave function for a single particle, if you then quantize that field psi as a field, you get quantum field theory and everything makes sense. Okay? And there's this awful name that's stuck to this. The name is second quantization. And it's really maybe the worst name in physics because it derives from a historical misunderstanding about the way that the quantum field theory should be thought of. We're not taking the wave function of quantum mechanics and quantizing it again, which is what second quantization implies. Okay, that's just not what's happening. What we're doing is we're taking a classical field and quantizing it once. Okay? Now, it turns out that in some situations, in non-relativistic cases, the equations of motion that were obeyed by that classical field also happen to be the same equations that arise for the Schrodinger equation. But you're not quantizing the wave function twice. You're not quantizing anything twice. You're not quantizing the wave function once. You're just quantizing the classical field once. Okay? So this name second quantization, it's a terrible name. It's still in use mostly in condensed matter physics, but it's a terrible name. Okay? Yeah. This field psi isn't Klein-Gordon. The Klein-Gordon field isn't. It becomes most clear when we've got all of these fields on equal footing. The Klein-Gordon field, the spinor field. The next guy is going to be the gauge field. That gives rise to electric and magnetic field. Nobody ever thought the electrical magnetic field had a wave function interpretation. Right? If you really want to put everything on equal footing, that's what you believe. And the reason is nothing has a wave function interpretation.
What about these U's and V's? Sometimes people call them the wave function.
Yeah. That's right. People talk about wave function renormalization, where when this gets changed, it's bad language that's left over for historians.
Yeah, we had a tutorial once where we took the Klein-Gordon equation and we recovered quantum mechanics from the scalar field. Is the same thing possible from this?
Absolutely. So you can take non-relativistic limits of this if you're interested in energies much lower than the masses. If you can guarantee that there's not going to be any pair creation of particles, you can then try to write down wave functions for one-particle states, and you'll get you'll recover the usual quantum mechanics.
With spin and everything?
Yeah, with spin and everything. Yeah, and the spin is, I rounded off the spin we got from sitting in here, and it already looks kind of like non-relativistic quantum mechanics. You know, this is a four-component object. Actually, it's got the same two-component object twice, and that two-component object is the same. So it's sitting in here.
If you remember Malcolm's last lecture, he took the non-relativistic limit of the Dirac equation coupled to a magnetic field. So it is all sort of in there. When he went to talk on about the anomalous, the magnetic moment, so the electron, he took a very careful non-relativistic limit. So it might be worth going back and reading that again.
Look when he did the iron off Tong.
No, after that, his last lecture when he talked about the magnetic moment showed that the Dirac equation predicts that it's correctly known.
G is 2 that comes out in this direction. I think that's what Dirac did. Actually, apparently, the day after he discovered it, and then thought his job was done for that day, and went to bed knowing full well that he would give the right answer. But he wanted to get G to balances. So he had a good night's sleep, and then woke up, and then showed that yes, G equals 2. But this idea of antiparticles, these kind of arguments, this took another 2 years from when Dirac wrote the equation to when he sort of understood the elements negative energy states, understood this argument. Originally, he wanted to interpret these as protons. He knew they had to have charge +1. And it looked as if they had to have the same mass as the electron, but he was hoping that somehow he could get around that and get their mass to grow so that they were protons. But this was back in the day when you didn't go around predicting new particles. He was very conservative about this. But then Oppenheimer and a couple of other people proved that it had to have the same mass as the electron. And then Dirac was the only one bold enough to say, well, there's going to be a new particle then. And it was discovered within a year or so. It was actually discovered by Dirac's colleagues down the road. Cambridge is a bit of an odd place to talk to each other. So the colleagues down the road, this Blackfin company, had no idea that Dirac had predicted this particle. And in fairness, it's not just that Cambridge is one place, it's that Dirac was an extremely odd human being. Or borderline autistic, I mean. So he didn't tell anybody, and it was Anderson at Caltech who discovered this particle. And then slowly word got around that there was an experiment and there was a prediction and that things matched. But yeah, Anderson didn't know that Dirac had predicted it when he made his discovery. Okay, so that's a little bit of a historical interlude, but I think it's important to get clear that second quantization ain't what's happening. Okay, just first quantization. So are there any questions about this? Okay, we're going to move on. We're now going to do exactly the same thing as we did for the scalar field, but we're going to do it much faster. Okay? So the first thing, remember we took the Schrödinger picture, we went to the Heisenberg picture. Okay, how do we go to the Heisenberg picture? All these squiggles, right, they go. Everything's, the operator depends on time. I know it's easier for me to do this on the board than in your notes, sorry. The other thing that happens is that the minus signs flip here. Okay, the reason the minus signs flip is because you still want this one to be minus I 3 momentum dotted with x, but because of this signature we're working, 4 momentum dotted with x has a minus sign for the 3 momentum. Okay, so this is the Heisenberg picture. Okay, what did we do then? We showed that this obeys the, for the scalar field, we showed that it, as an operator, it obeys the Klein-Gordon equation. Okay, the same thing works here. As an operator field, it obeys the Dirac equation. We also worked hard to make sure that things commuted at space-like separations for the bosonic field. So you can show something similar here. And you know what can show that means, right? This is all all of these things that I'm encouraging you to do, they're all in the notes in glorious detail. So, but it is worth working through them. OK, so you can show that these fields in the Heisenberg picture have this special property at space-like distances, but they don't commute with each other. In fact, they anti-commute with each other. Now, you know, when you say that there's no causal propagation, it's really a statement that operators commute like at space-like distances. And here we find two operators that don't commute at space-like distances. They anti-commute. Now, there are words you can say around this to make yourself comfortable. The kind of words are that, well, we never actually measure psi directly. What we measure are things like psi, dagger psi, you know, bilinears of psi. And those things all commute amongst themselves. You know, nobody's ever, the words you're supposed to say at this point is that, well, nobody's ever made an experiment, measured an experiment which is a Grassmann-valued object, or a spinor-valued object. In particular, if you make an experimental measurement, you measure something, and then you rotate by 2 pi, you know, the number isn't minus itself. The number is modulo my silly experiment the other day. OK, so there are words you can drape around this. I have to say, if I was at all interested in, say, foundations of quantum mechanics and, you know, the deep things that people think about here, I'd probably think much, much harder about this. I find this a little bit puzzling myself, but maybe that's just me. But it doesn't commute at space-like distances, it anti-commutes. Yeah? Yeah, that's probably right. Thanks. OK, we can define various propagators. Let me just jump straight to the one that's relevant, which is the Feynman propagator. So the Feynman propagator I'm going to call S. S for spinor, F for Feynman, alpha and beta for the spinor indices. Okay? And I'm going to define this to be
two field operators that have to communicate.
yeah, so I'm going to define this to be, you guys,
Different space-time points. This is in the Heisenberg. It's the same thing you're doing. But we didn't have Jacob. All right.
is there no dagger? Let me just check. Yeah, there's no dagger. Sorry, that's right. Yeah, there's no dagger. Sorry, you're absolutely right. In the Schrödinger picture, these things trivially commute. But where this is x and this is y, but at equal times. That's the point. Equal time commutation relations, or in this case, anti-commutation. So here the question is, do they commute at arbitrary times outside the light time? And the answer is no, they anti-commute. Thanks. OK, I'm going to define the Feynman propagator to be the time-ordered product of psi and psi dagger. Okay. And there's a small subtlety in what I mean by time ordering, and the subtlety is this minus sign subtlety. Okay. It's that time ordering doesn't quite involve just placing the one at later time to the right. But if in doing that you have to move this guy past this guy, you pick up a minus sign for your troubles, okay? And the minus sign is because these guys anti-commute instead of commute. Oh, thanks, yeah, so there's an alpha and a beta on X.
And we switched to the Dirac conjugate because we went to the Heisenberg picture.
Yeah, we put the Dirac conjugate in here. Why have we done that? In some sense, you could think of it as that's just a definition. The real question is why it's the useful definition. And it will prove to be the useful definition when we can do Feynman diagrams and do mixed theorem.
So they don't commute in the time ordering thing anymore.
Good.
And so where would you move the gamma zero matrix? Like,
Oh,
can they just
that's
anti-commute? And
no, because they're not multiplied together with their spinor indices. The spinor indices are left angle.
Okay, yeah, but you have a gamma zero on the right, really, right? You have like gamma b dagger gamma zero. That's the Dirac.
Yeah, so psi dagger beta is psi dagger alpha. Again, it doesn't really matter where alpha beta. I should call it gamma maybe. No, I should I'll call it delta. I don't want to confuse it with that. Okay. So this whole thing is sitting in here.
Okay.
And this index is just left.
But just, I guess when you would anti-commute the whole thing.
Yeah, this whole thing goes.
Okay.
And why is there not like a gamma zero going about over on?
There's not one here, but I could, if I wrote this as psi bar, I just have to put a gamma zero on the right hand side.
Yeah.
So yeah, and this is really just the conjugate of this at the moment. The place that psi bar appears is when we start considering the action.
Oh.
But then, those Hamiltonian interactions are the things that we have to flip between time ordering and normal ordering. They have psi bars in. That's why this is really useful.
One last question.
Yeah.
Does the Dirac conjugate generalize the idea of unitarity to metric spaces? Because we introduced it so that we could recover a kind of unitarity.
Yeah, what we allowed is that a kind of, yeah, so this was invariant until the psi goes to S psi, even though S always used that was the. Okay, as always, there's a nice integral representation of this. So read, you, and show that. This is the same kind of thing we had for this is exactly the same kind of thing we had for the scalar field. The I epsilon there dictates the contour we take to avoid the pole when we do the P0 integration. But what's novel is that there's a P slash plus M that sits at the top here. Remember, P slash is now a 4x4 matrix. It's the momentum P multiplied by the gamma matrices. So one reason you can see that there's a P slash at the top there is that this is a Green's function for the Dirac equation. What that means is if I take the Dirac operator and I hit on fitted on this propagator, I get the delta function coming out. Okay? Again, that's exactly the same as for the Klein-Gordon equation. But notice that this is a first-order operator now, not a second-order operator. So this should roughly be 1 over p, not 1 over p squared. And that's what we see. There's a 1 over p squared, but there's a p on the top. Yeah. Okay. Wick's theorem. We define the contraction between two operators to be the difference between the time ordering of the operators and the normal ordering of the operators. Okay. Notice that this is the time ordering of the operators, not the operators sandwiched between the vacuum state. Okay.
That's not far.
And this is just equal to this propagator. Okay. Same thing that we saw for the scalar fields. Okay, so what do? You go through Wick's theorem, you have your interaction Hamiltonian, you want to compute, because of Dyson's formula, time-ordered products of a bunch of fields. The way to compute it is to shuffle everything around so that there's annihilation operators killing things. If you do that, Wick's theorem tells you that you have to do all these contractions. The contractions give you the propagators, and so on. Okay. Rather than going through a long, tedious example, which I could do and it's in the notes, but you thought it was bad for the scalar field. It's much worse because we've got all these spinor indices hanging around. What I'm going to do is give you a particular theory that's extremely interesting, and then tell you what the Feynman rules are for that theory, and then maybe try and answer some questions about why they're the Feynman rules and how we can see things arising. Okay? Okay, so the theory we're going to consider is Yukawa theory. And it's going to be a single real scalar field and I'm going to call the mass mu. And then I'm going to add to this a Dirac fermion whose mass is m. And this interaction. Okay. Okay, so remember we looked at very similar things when we were thinking about a complex scalar field interacting with a scalar. That was sort of a baby version that was just building up to this particular interaction. Okay? There are interactions of exactly this type in the standard model. Okay? The psi's are the fermions that you know and love. They're the electrons, the muons, the taus, the quarks. And the phi here is the Higgs field, okay, in that context. So the things we're going to compute are really relevant to the best theory we currently have. So this is the Yukawa interaction. Let me just do this simple dimensional analysis. So remember, the way this works is that the Lagrangians should have dimension 4, precisely so the action has dimension 0 when we integrate it over 4 space. So we know that this has 2 derivatives, so each of these has dimension 2, which means phi has to have dimension 1. So this is the canonical dimension for all scalar fields in 4 dimensions. But what about the fermions? Well, this has dimension 1. It's a mass, so you would hope that also has dimension 1. Which means the psi's have to have dimension 4 minus 1 equals 3 for the two of them. Or in other words, psi has dimension 3/2. Okay? Again, this is the canonical dimension for fermions in 4 dimensions. So now let's look at this term. We've got 2 psi's, which gives us 3, plus a phi, which gives us 4, which means that this is a dimensionless coupling. So the dimension of lambda is 0. So this lambda, this Yukawa coupling between 2 fermions in a scalar is just a number. And in order for this theory to be weakly coupled, this number has to be small. Okay? In the real world, it is small. I think it goes down to about 10 to the minus 6 for the electron coupling to the Higgs. I have a feeling that for the top coupling to the Higgs, this number is almost exactly 1. Nobody knows why that is. I don't think there's any theory about why it would be exactly 1. But okay, so is this clear? Yeah. Dimension 3 over 2. In 3 plus 1 dimensions. It required that this L was. So if you're in, well, there's a whole course's worth of answers to this. If you're in different dimensions, then it's different. But it's also true that this is sort of what's called the classical dimension. These numbers can get quantum corrections. And actually, that's where a lot of the interesting physics is. Yeah, there are things called anomalous dimensions, which you'll learn about in the next QFT course. Okay. So I'm not going to go through an example. What I'm going to do is just tell you the Feynman rules. And then we'll compute things. Oh, perfect. Okay, so you do the same thing as we did before. You're interested in some scattering experiment where you're going to say what's coming in and say what's going out. You draw those things going out and things coming in as external legs on the Feynman diagrams. Then you have to connect everything together, and you connect everything together with a trivalent vertex that has 2 fermions and a scale. Okay? So yeah, the extra things we need to know is how to label the particles to say what their spin is. Okay, so whether it's spin up or spin down that's coming in, because that's going to be sort of the key crucial physics. So to each incoming fermion, with momentum P and spin S, we associate this particular spinner. Okay, so this is a fixed spinner. Okay, so this is a particle coming in. Eventually it's got to do something, but as it comes in, its momentum is P, and we just write down US of P in our equation. Okay? And for outgoing, we write down U bar of S. Okay. This might seem a bit arbitrary, but again, it comes from doing Wick's theorem 3 times and realizing that there's just this algorithm to computing these things. So it's maybe worth you doing it once, just check that this isn't totally crazy. But I'll write it down and then try and give you some understanding about where it comes from. If we have incoming or outgoing antifermions we're going to add V bar of P or V. So notice that there's actually a flip here. For antifermions, the incoming ones have V bar, and the outgoing ones have V. Whereas it's not just the U and the V that flip, it's the bar and the unbarred that also flip. Notice that this is an incoming guy, which is labeled by this P, so it's going that way, but this arrow goes the opposite way. And this arrow, remember, is telling you the charge of the state. So this is saying that it's an antifermion instead of a fermion.
What kind of a charge, since we haven't really gotten to electric charge?
Good. So I said it briefly, but I didn't really stress it. There's a symmetry, which is this, and the current associated to this is this, and the charge is always the integral of the zeroth component of the current, and it's basically going to be the number of C's minus the plus or minus. It's going to work out to be the same thing we saw in, yeah. Sorry, I should have. This whole Dirac part of the course, it's so much. Let's do what we did before, but do it again. That I don't want to go through everything on the board, but
sure
yeah. So I missed this, but yeah, it's exactly the same as what we saw before. Yeah, this is the part of the course I'm doing much faster than I would like to be doing.
But sorry for interruptions.
No, not at all. I encourage more. Each vertex gets a factor minus I lambda. Okay? This is the vertex. There's a minus I lambda, and that's precisely because there was a lambda was what is the coupling constant in front of the Yukawa term. And then there's the internal lines. So for scalars, what you add to the internal line is the scalar propagator that we've seen already. For fermions, it's the propagator that we just came across. Then there's the other kind of rules that we always have. You impose momentum conservation at each vertex, and you're going to integrate over any unresolved momenta, so momenta running in loops. And finally, there's a whole bunch of extra minus signs that arise. And these extra minus signs arise basically because if you're inside time-ordered products or normal-ordered products, everything that you thought commuted actually anti-commutes, and you pick up lots of minus signs. Okay? Now, rather than give you rules for how to do this, well, the rules for how to be sure about the minus signs is to go back to Wick's theorem and do things carefully and figure out the minus signs. Suspect that with enough practice for any given Feynman diagram, you can just work out the minus signs. I'm not sure I've had enough practice to do it for complicated Feynman diagrams. Okay, so these are the rules. So what I want to do now is just give you some examples. Yeah, Bruno.
Why isn't there a semblance, like the Riemann propagator should depend on the incoming outcome?
Ah, good. So what's going on here? So this is actually a matrix, okay, a 4x4 matrix, because there's a p slash. So it has an alpha beta that I've just left dangling. So the question is, where is that? What's that matrix going to multiply? So let's say this is an internal line and it has a matrix. It's going to hit some other line. If this is another internal line, it also has a 4x4 matrix. Okay, so this keeps going until finally you hit an external line. But the external lines come with either a U or a U bar or a V or a V bar. And the way that they've been ingeniously designed is so that it's always going to be such that you end up with something which is a number and not a matrix. Okay? And I'll give examples now about how that works. If you get a closed fermion loop, then you've got a trace over spins. Absolutely, yeah. Sorry, yeah, that's right. But you can kind of see that because this is a matrix that joins up this side, and that's what's meant by a trace.
Wait, why are the arrows pointing?
Yeah, thank you.
Oh, okay, sorry.
No, I just screwed up. Yeah. So the example I want to do is something we did in the scalar case in some detail. It's nucleon scattering. Okay. P1, sorry, P and S coming this way, P prime and S prime coming this way.
So it's to be understood that in the graph diagram, the two don't actually.
Yeah, so it jumps over. I'll explain why I drawn it this way. Okay, these, believe it or not, are the same two diagrams we had in the scalar case. Remember, in the scalar case, I drew them both like this, and I just flipped the labels on this. This I called P prime, sorry, this I called Q prime for the second diagram, and this became P prime. By the way, the R and the S are just the spinner indices of one. This is exactly the same diagram. You know, it's sort of the which direction you draw these things coming out in it, that doesn't have any physical significance. It's really the sort of the labels you use. So the reason I've drawn it this way, and I could have just as well sort of drawn it this way, where this is Q, this is P, it's to emphasize the fact that this diagram and this diagram just differ by flipping around the P prime and the Q prime. And that's like exchanging those particles. And in particular, that means that this diagram has to pick up an extra minus sign relative to this diagram to impose Fermi statistics. Now, if we go through Wick's theorem, yes, you'll see that minus sign up there. But this is the kind of thing I meant when I said add extra minus signs on the prime. This is an example where we have to add extra. So what's the amplitude for this? Well, we follow the Feynman rules. There's two vertices, so that comes with a lambda squared. And now comes this, well, let me write it down. But all the new stuff is basically in how the spinor indices contract with each other.
What is that on the top? With this? So UP prime dot.
Or P prime dot with UP and UQ prime dot with UQ. Where the U's are these fixed matrices here. And you can just write them down. So there's some fixed 4 vectors, 4 spins, functions of the T's, and also the spin. Okay, so where are these? So firstly, this guy here on the denominator, this is just the propagator of this that should be clear. This minus sign is because these should have only statistics instead of those statistics. So all the new stuff is basically in the fact that these guys are contracted together. And this is telling you sort of the spin dependence of the scattering amplitude. You know, if I get 2 spin-up particles coming in and they scatter, that's going to be very different amplitude than if I have a spin-up and a spin-down. Or at least potentially could be. So that information is included here. Okay? So why is this coming? These are coming from the Feynman rules that I told you about. So for every incoming particle, you write a U, and for every outgoing particle, you write a U bar, and then you contract them accordingly. So this is U bar contracted with this U, and, well, so on and so on. Okay? Why are these things arising? You know, remember what's happening is that this is basically Wick's theorem. So we've got this time-ordered product of a bunch of fields, which in this case are the Yukawa interactions, psi bar, psi phi. Okay? All of those psis have creation and annihilation operators in, but they also have these u's and v's floating around. So when we're commuting things past each other, those creation and annihilation operators are shifting, but the u's and v's are just sort of hanging around, lying there. And those Feynman rules tell us what to do with them and how to bring them out. Okay? It's not, hopefully not conceptually difficult, but it's a real pain to actually write these things out and get everything right. There's a bunch more examples I can do, but basically I'll just be writing equations like this on the board, and they're all in the notes, so it's probably best just to sit down and familiarize yourself with how these spinners arise here. Okay? And the next 2 lectures we're going to move on and do QED. So this is basically it for Dirac. So are there any questions before we move on? Yeah.
So I don't think it matters where the minus sign actually is. So presumably if we do the Wick's theorem thing, the minus sign is not static first. So how do you know that?
Oh, yeah, whether or not I've got this minus sign right. Yeah, I remember this is a good question because yeah, when I was teaching this course for a couple of years, I think it was only at the end of the second year I got my minus sign right. Not for this calculation, but for nucleon anti-nucleon scattering. And actually, I think it is important here because I think it feeds in. Oh, no, I remember. So it doesn't matter at all because there's a step. You just square it, right? But I have a feeling that the relative minus sign between the nucleon scattering and the nucleon anti-nucleon scattering in the overall amplitude is what tells you whether they're both attractive or one's attractive and one's repulsive. So I think these overall minus signs are important. I might be misremembering. You basically have to sit down with a big cup of coffee and a large sheet of paper and play through Wick's theorem. Okay. There may be tricks. I don't know. The way I have to do it is play through Wick's theorem if I really appreciate it. Other questions?